Okay, thank you for tuning into Transparent Physics. This is the third in our series of uniform circular motion problems moving in circles. This problem is going to be a little bit more advanced. It's going to require a little bit of physics that you probably learned earlier in the year. And we'll see how our new equations dovetail in with some physics you already know. Take a quick break here. All right, let's get started. So, we start with a 1986 Nissan Pulsar, truly one of the great cars in world history. It takes a hard left turn at an intersection, making a turn of radius 11.2 meters with a constant speed. If the coefficient of static friction between the tires and the road is equal to 0.72, what is the maximum speed in miles per hour that the Pulsar can take the turn at without skidding? And if the pavement was wet and μs dropped to 0.36, which is half of the initial value, what impact would that have on Vmax? So that's a lot going on in that problem. We're going to have a lot to unpack as we work through. But let's get started. So I got my quips snacks here. So we have read the question, and peace. That's right, peace. Can't argue with that. Underline. Now, don't just randomly underline something. Just because this is a number, it doesn't mean it's important. Now, 1986, a great year, but it doesn't really help us with the problem. So just move past that. We got a radius here of the turn. Constant speed. Again, everything you work is going to have a constant speed at this level. Coefficient of static friction. That's an indication of how well the tires grip the road. And we're interested in the maximum speed. And note that they do want it as miles per hour. That's going to be a classic mistake kids are going to make. They will solve for the maximum speed, but then forget to go back and convert it to miles per hour. That the Pulsar can take the turn at without skidding. Basically, you're saying, hey, if friction is the centripetal force, what speed can you make with? So without skidding means you're going to be using the static friction. And then, so this is really part A. And then we'll make this into part B. And if the pavement was wet and we dropped mu, impact would that have on Vmax? So actually, part B doesn't really look that bad, because basically they're just saying, hey, take the same situation, but have a lower coefficient of friction. What's that going to do to your speed? By this point, when we get to B, we'll have already figured out the mathematical relationship. So we should be able to relatively quickly update that. But we'll see. If you have half the friction that you started with, is that going to mean that you're only going to be able to take the turn at half the speed? Well, let's find out. Okay, so take a quick sip, and we'll get. So we underlined. So since we underlined already, yes, that's a repeat. Still sweet, but a repeat. All right, information. And this one's a little bit harder to draw because we've got an object turning. If we do an overhead view, so what do we have? We have like an intersection, and the car is taking the turn in the intersection. So it's taking a hard left. So we've got the Nissan Pulsar here, and it's going to turn like this with a constant radius. So the radius is somewhere around here, and we don't know what the speed is. So we do not know the speed of the object as it takes the turn. They don't really give us a lot. They tell us that the radius is 11.2 meters, which is good. We know μs is 0.72, which is pretty average for tires on road, so not unrealistic. So that's about it. Conspicuously missing is the mass of the Nissan Pulsar 2. So they really don't give us a lot to work with at all. So it'll be interesting to see how that works out. But I guess that's all the information. So since we've got all of our information down, time for our next one. BFF, yeah, I'd like to, BFF, I could be nice if we had some more information. But we can still be friends. All right. Well, we're going to hope the problem works itself out for us here. Let's take a look here. Next up is the procedure. When we have friction, taking a turn like this, if friction is acting on the car, so we can add another picture here. So the car is going around the turn. And there needs to be a force acting towards the center in order to make that happen. Now, that force is what we call the centripetal force. Now, the centripetal force is served by different forces depending on the scenario. In this case, a car rounding a turn, the frictional force is going to be provided by, or the centripetal force is going to be provided by the friction. And we'll just say static friction for that. Now, while we're at it, there's other things going on with this car. There's an upward force on it and a downward force on it. The upward force is the force from the road. We're going to call that the normal force. The downward force is the force of the weight. So these three forces act together on the car to keep the car going around the turn. Well, these three forces act on the car. We'll leave it at that. Really, it's only the force acting towards the center that really acts to keep it going around the turn. But that is the centripetal force. So this is a top view. This is a side view. And when we have these sort of arrangement of forces, it looks like it's a two-dimensional force analysis problem. We can use a vector analysis table for. Ultimately, we are interested in the speed. Now, if we knew the force pulling towards the center, we could use the relationship that FC equals MAC. And then wherever there is AC, we could read it as FC equals mv squared over r, because AC is v squared over r. These are equivalent to each other. So, if we knew the centripetal force, we'd be closer to knowing the speed. We know the radius. So can we figure out the centripetal force from this scenario? It's hard still because we don't know that mass yet. So maybe still a little bit confusing, but let's just have faith that the problem's going to work out nonetheless. This might be a bit more of a formula-heavy problem than it is going to be just plugging in the numbers. And that's something we need to get used to in physics sometimes. Sometimes you're not going to have the numbers to plug in immediately. You're just going to have to sort of take a leap of faith with the equations and hope that it works out. Either A, what you weren't given is going to turn out to be non-important anyway, or B, you missed something, or the person who wrote the problem missed something. One of those three. So let's just follow through. So in this case, we are going to be interested in setting up and solving the information that we can get. So I think we're going to draw a vector analysis table here and see where we can get as far as that goes. So we have three forces. And we're going to set these up to analyze these. We're going to list our normal force at 90 degrees. We're going to list the frictional force at 180 degrees. And we're going to list the weight at 270 degrees. And so we have fx equals f cosine theta. We're going to solve all these with respect to the positive x-axis. by this point in the year, you've maybe already done two-dimensional force analysis, but so hopefully this isn't the first time you're seeing it. All right, so what do we got? And we want to ask ourselves the question. The question is whether or not there's acceleration. Now, there's no acceleration up and down. We'll just say it's an unbanked curve, etc. It's just staying on the road. So there's no acceleration. So the forces are balanced in the y direction. Are the forces balanced in the x direction? No, because you need an unbalanced force pulling you towards the center. So since the forces are unbalanced in the x direction, there is an acceleration going towards the center of the curve. If you have an acceleration, you have an unbalanced force. So we can write that. Okay. If we look at this a little bit further, we can do the math. If it's straight up and down, there's no component in the x direction. If it's left and right, there's no component in the y direction. If it's up and down again, there's no component in the x direction. So the sine of 90 is 1. So 1 times Fn is Fn. The cosine of 180 is negative 1. So this becomes a negative, and we can just write the coefficient in there because we have an equation from earlier in the year that the friction is equal to mu times the normal force. So wherever I see the friction, I can replace it by the normal force, which I just did right there. And then the weight is going to be sine of 270, which is negative 1, times the weight, which is negative mg. All right. Well, what do we know? If we take a look at the information, it still seems like there's a lot that we do not know yet, but let's just have some faith. If we take a look here, we've got the x column, we've got the y column. We'll start with the y column. In the y column, we'll pull a formula out of there. We have Fn minus mg equals 0 newtons. Zoom in a little bit on that. So we know that the normal force is opposite the weight and equal in magnitude, which is good. I mean, that's good. We don't know the mass yet, so we don't actually know the normal force. Now, in the y direction, the fact that this is a negative is not critical, I would say, for this problem, because we could draw the circle the other direction and it would have ended up being positive. Normally, we have to be pretty careful as far as the signs go. But realistically speaking, if the force was pulling in the negative direction, we would also get a negative value for the acceleration. So this plus this plus this equals this. And what we'll just do here is I'm just going to put absolute values around everything. So we'll just drop, technically there's a negative sign associated with this acceleration and a negative sign associated with this force. We'll just have them drop out. And it still seems like a lot that we don't know, but we do know that wherever we have a normal force, it's equal to mg. So there's a normal force right here. So we can say mu s times the quantity mg equals mac, and take a look at that. Because mass appears on both sides, it cancels out, so we never needed it anyway. And we know mu s and we know g. So at this point, we actually have enough information to solve for the acceleration. So by not plugging in the values, we were able to focus on just working with the equations, and just working with the equations. Stuff dropped out, and we end up with a very, very simple calculation to end up with. The acceleration is simply mu times g. And mu is 0.72. There's no units for mu. G is negative 9.80 meters per second squared. And we'll just do a quick calculation on that one, see what we get. Now, this is not the answer, but this is an important moment in the history of our answer. So 0.72 times 9.8. Let's say 7.1 meters per second squared. Now I'm not even going to circle that because that's not our answer. That simply gets us to the acceleration. Now if we know the acceleration, we are interested in solving for the if we know the acceleration, we're interested in solving for the speed. So the quickest connection between acceleration and speed is going to simply be the relationship AC equals v squared over r. Can't get much faster than that. We did manipulate that in an earlier video. Step by step, this equation turns into AC times R equals V squared. And then if we isolate that for V, we have V is the square root of AC times R. And we know AC and we know R, so I feel like we're in pretty good shape for this answer. So V is the square root of 7.1 meters per second squared. Radius is 11.2 meters. So multiply those two together. Don't forget to take your square roots, and we'll be good to go. So square root of 7.1 times 11.2. And we get a speed of 8.9 meters per second. Now, is that the answer? No. Because don't forget, when we set this problem up initially, they did want to know the maximum speed in miles per hour. So that's really something we should have listed in our diagram in terms of an end goal that we're looking for. So this is going to be a little bit of unit conversion to end up with. Again, a classic opportunity to miss some points here. So we have 8.9 meters per second. A little factor label conversion to get us across the home stretch. Move my T out of the way. Okay, so we want to, I'm going to say this is going to be a two-step solution here. We want to take meters to miles. So there are 1609 meters per mile. And seconds to hours. And there's 3600 seconds per hour. So we'll calculate off screen here, but it's 8.9 divided by 1609 times 3600. And that's about 19.9 miles per hour. Let's just say 20. All right. So that is how fast you can take that turn without skidding. Okay. So it's not crazy. Of course, it's a pretty tight turn. So 20 miles per hour. Not unreasonable to imagine that you wouldn't be able to take that turn that fast. And I feel like we're not done yet, but I feel like we did do the procedure, so let's just get this done. So a little hard to make that out. I see an SWE. That could be the Society of Women Engineers, a great organization to get involved with if you're planning to go into engineering and you are a female. So Society of Women Engineers, we'll just assume that's the one. All right. So no, we're not done with the problem, but I think we're pretty done with the problem. So the problem is basically saying, hey, do this whole thing again, but instead use mu to be 0.36 as opposed to 0.72. So just think to yourself for a minute, if you had half of the friction, what do you think? Is the speed going to be half as much? More than half? Less than half? What things factor in to make you say what you think? Do note that we're a little complicated here by that a is v squared over r. So anytime you have square roots or squared, it's not necessarily just, well, it's not going to be a linear relationship between those values sometimes. So we don't have to rework the entire problem again. I'll just do a little side screen here between the two of them. We are going to, I'll switch colors. Everything's the same until we actually plug in the values. That's another advantage of working with equations as late as you can. You can follow it through pretty far. So our new mu, maybe I need to zoom in a little bit. All right, our new mu is going to be 0.36. So that's going to change this value right here. So our new AC, we'll call it AC prime, is going to be mu s times g, and that is instead going to be 0.36 times 9.80 meters per second squared. So obviously we're going to end up with a smaller value for that. So the original problem had it as 7.1 meters per second. We're going to get half that much, so times 9.8. So around 3 well, pretty close to that. So we'll say 3.5. Okay. So armed with a lower acceleration, we're going to plug that into this equation and see the impact it gives us on the velocity. Last time we did this, we got an answer of 8.9. Radius is still unchanged. And last time we did this, we got 8.9 meters per second. This time, it ends up being 6.3 meters per second. So it's interesting that the value went down, right? But it's not half of what it used to be. The idea is that speed is very important in determining how easy it is to round a turn. So if your speed drops, it makes it much easier to round a turn than if your speed is high. So we can do the conversion. I'm not going to work out the math for you, but 6.3 meters per second, if we run it through the same formula that we did last time, divided by 1609, multiplied by 3600. So you're going to get around 14 miles per hour around the turn. So having the coefficient of friction does not actually have the speed that you can get around it with. So again, interesting things happen when you have squares and square roots and things like that. So I think we wrap this problem up. A little off center there, little quality control issues. I'm going to say gal-pal, maybe? Gal-pal? Sure. So I don't have anything to say about that. I don't know. So this problem definitely hardest out of the set. Brought in some physics from previous units, but at its heart, when we actually did the uniform circular motion equations, they integrated in, I think, pretty smoothly into the physics we already had. Important thing to take a note is that the centripetal acceleration is provided by another force. In this case, it is the friction. The friction pulls you towards the center to allow you to round the turn. This reminds me of I think it was one of the Batman movies from like the late 80s, the ones with like Michael Keaton and George Clooney and stuff like that. And there was a scene where the Batmobile was rounding a corner in Gotham City, and it wanted to take a turn very quickly. So it fired a bat cable out and hit a lamppost that was there, and then it used that to spin itself around the corner very quickly. Now, there's not much I can say. Those movies were pretty cheesy, but that was actually some decent physics. If you can actually make the shot, tie your cable around a street lamp, you can use that to provide additional force pulling you towards the center so you could take the turn faster than you would otherwise. That's the same reason why if you're going down a set of stairs real quick and you have to make a turn while you're going down the steps, you grab onto the handrail, because the handrail pulls you inward and allows you to make a tighter turn as you round the corner going down the steps. So physics everywhere. I hope you've enjoyed the opportunity to see a more challenging problem worked out and how we can bring in physics from earlier units that ties in to the physics we're doing now. And I appreciate you taking the time to join us on this lesson of transparent physics, and hopefully we've made things a little clearer for you. Whew. Have a good one.